All right, guys, we are back for another subsection all about quantitative data analysis. And in this subsection, I'm going to be teaching you just the basics of regression, which is a statistical analysis technique where we can take two or more variables and try to determine whether there is a relationship or a correlation between those two or three or more variables to see whether there is an actual relationship there or not, right? So when it comes to regression, there are lots of different kinds. Okay, there's logistic regression and just there's a whole bunch of different ones, and each one is appropriate in a slightly different circumstance. Okay, the one I'm going to be talking about here is called OLS, or ordinary least squares. Okay. And for ordinary least squares regression, basically the way you can think of it, we can start out with something like this scatter plot we have in this image here, right? So with this scatter plot, we've got height along the x-axis, we've got weight along the y-axis, and we have what looks to be about 24 different people who had their height and weight measured, and each person had a dot put in the place that their particular values fell, right? Now, just glancing at this scatter plot, does it really just kind of look to you like there seems to be a relationship between height and weight? Or is it completely random? Well, to me, it looks like there might be a relationship, right? There's much larger clusters in the lower left and upper right, which would indicate a positive relationship, i.e. as height increases, weight increases. Is it perfect? Obviously not. There are tons of outliers there, right? But with OLS, what we want to do is draw a line, a straight line, somewhere on this scatter plot, in some orientation, but from one end to the other, where that line has the smallest combined distance between the points and the line. So what we could do theoretically is just draw an infinite number of lines at different angles, you know, like this angle and 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 this, and then add up the distance between the dots and the line for all of those different possible lines. Or we could just use a computer program, set it to do ordinary least squares regression, and figure out which of those lines from here to here to here to here, you know, which one of these lines is going to have the smallest combined distance between all of the dots and that line, right? So we've got that same scatter plot here, right? If there was absolutely no effect, if height and weight were completely unrelated, we would expect a horizontal line, right? If a horizontal line is your best fit, then obviously your x variable and your y variable have no real relationship, right? So if we want to show a relationship, like we might here versus with height and weight, we want to calculate what the most correct line is, what the line is that has the smallest combined distance between all the points in the line. And we want to know how confident are we that this line is actually the best fit for this data. Like, how sure are we that in reality it's not actually a flat line? It's just by sheer random chance we get a slightly upturned or downturned line. But, you know, if we had more data, if we had more experience with the real world, would we still see this angled line, whether it's this angle or that angle? Or would it really be flat? So in other words, is this line we're seeing that's off from flat due to sheer random chance? And just the fact that we got a group of people who happen to show that there is the line is off from horizontal, or is that not because in reality the line is off from horizontal? It's just due to sheer random chance, the group of people we had. Okay. Now, in order to use this OLS process, we have to have what's called a continuous dependent variable, right? So in this example, our dependent variable would be weight, because we want to see the relation, x is height, y is weight, and our y variable is our dependent variable. So our dependent variable is weight, and we have to measure that as a continuous variable, i.e. there's lots and lots and lots of values. We can measure weight both as 170 or 142.5 or whatever. If we only had like 3 or 4 or 5 different values, God forbid 2 different values for our dependent variable, then we couldn't use OLS. We would have to use a different kind of regression. Okay. So if our dependent variable was like a yes or no question, right? We want to know whether, whether having a college degree makes you more likely to be a criminal. And our criminal dependent variable there was measured just as yes, you've been arrested, or no, you haven't been arrested. We couldn't use OLS regression on that because the dependent variable there is dichotomous. It's only got 2 different values. To use OLS, our dependent variable has to be continuous and have tons and tons of different values, or at least possible values, right? Now, interestingly, OLS is pretty easy to think about when you've only got the one independent variable and one dependent variable, because the human brain thinks in 2 dimensions much easier. But we could theoretically add another independent variable. So what else do you think might impact weight? Right? Maybe it's, we think height obviously impacts weight, but we also think, amount of exercise you get every day impacts weight. So we add a third variable. But now we have to imagine this, and this is where it gets a little difficult, where we have that third variable, so we're going to have a third axis, and that axis is going to be coming out from the screen towards you. It's going to be the z-axis, right? And now not only are points for each individual plotted in 2-dimensional space, the way they are in the scatter plot, but they're also in 3-dimensional space, where not only are they, somewhere in this direction and somewhere in this direction, but they're also somewhere in this direction, right? So now we have a 3-dimensional scatter plot of values, where this direction measures height, this direction measures weight, and then this direction measures amount of exercise, right? And we can still draw a straight line that best fits the points. But now instead of doing it in 2 dimensions on a piece of paper, we're doing it in 3 dimensions with this 3-dimensional model. Now, contrary to what is really outside the realm of the human brain, we can do it in even more dimensions than that. We could theoretically have a whole bunch of independent variables. And we just have to calculate this line in kind of multi-dimensional space. And it's really hard for the human brain to get around that, but it's easy for the mathematics involved, right? So with OLS, we can have a whole bunch of independent variables. And we just have to kind of add a dimension every time we add a variable, right? As long as we still only have that one dependent variable, we can throw in a whole bunch of independent variables and then gauge how each one of those independent variables affects the dependent variable while controlling for all of our other independent variables, right? This is why adding in control variables is so easy mathematically. You just add them in as an extra dependent variable, and the way the math works, it controls for that effect, and we can only look at the effect of each independent variable on the dependent variable, rather than having to adjust for, age or population size or whatever, right? Now, one of the biggest things you have to worry about in OLS regression is collinearity. Meaning if you have 2 different independent variables that are either really, really similar or the same, you're going to run into a problem. So let's say, for instance, you put in as an independent variable age, and then you put in another independent variable that is year of birth. While technically you can think of them as two different things, they're the exact same data. A computer program is not going to know the difference, right? And so if it's, January 1st or December 31st and everybody has had their birthday for the year, those two data sets, age and year of birth, are going to be exactly the same. And luckily, the computer program that you're trying to do this analysis on will spit out like, hey, you've got a problem here. You inserted the same variable twice. And it won't let you kind of continue. But if you do it on any other day besides January 1st or December 31st, now you've got a bigger problem. Because while they might be really, really, really close, they're not exactly the same, and thus the computer program you're using won't notice the problem, but it's going to completely screw up your analyses. It's going to make all your conclusions really wonky, but you might not notice. So when you're doing an ordinary least squares regression model, you have to do a test for collinearity before you actually kind of make any conclusions about your actual independent variable, dependent variable relationship. Okay? Now here's one last example. All right? This is a scatter plot where along the x-axis we have chocolate consumption measured in kilograms per year per person. And then along the y-axis we have Nobel laureates per 10 million population. And as you can see, this is not a random scatter plot. This seems very clear that there is a line that is not a horizontal line that will much more closely fit this data at, an almost exact, lower left to top right angle that will fit that data and have a much smaller combined distance between each data point and the line than a horizontal line would. But do we really think that chocolate consumption affects your ability to win a Nobel Prize? Probably not. This is almost definitely an example of what's called a spurious relationship, right? Where there's some other factor that is affecting both chocolate consumption and ability to win a Nobel Prize, right? It might just be gross domestic product, right? How rich is a country? Because the richer you are, obviously, or usually, the more chocolate people are going to be able to afford. And the richer you are, the more you can invest in education and science and stuff, thus the more likely you are to win a Nobel Prize. So it might be something as simple as average income or national income or something like that, right? But it might not. Who knows? So, but I would bet any money you want to name that it's not directly chocolate consumption increasing the ability to win a Nobel Prize. Now, the last thing here, and when you read published literature, like an actual peer-reviewed journal article, very often they won't show you scatter plots and lines and pretty graphs. Or if they do, they're also going to show you kind of the same information, but shown in a table like this. And this table I copy and pasted directly from one of my grad school homework exercises. Okay, so it's an OLS, ordinary least squares, regression equation, explaining the marijuana use rate using real-world data from some public survey. And as you can see on this it's been a long day. On this table, we have 4 variables listed. The top one is the peer delinquency score. Then below that is age. Below that is sex rate, which in this case just means gender. And then below that is constant. All right. Now the first thing to know is that the constant is going to appear everywhere. That is just a measure of, if whatever line you've drawn, at what value does that cross the y-axis, right? So if you theoretically drew that line through an infinite two-dimensional plane, at what point on the y-axis would that line hit? Okay? So all that's telling you is that for a theoretical value, zero value of x, where does this line you've drawn hit the y-axis? So every OLS equation is going to have a constant there. I've even seen it sometimes just not reported because it's relatively difficult to interpret and doesn't really matter as much as all those other ones, right? So remember, we have our dependent variable here is marijuana use. How much do you use marijuana? I think, I can't remember exactly, this was a long time ago I actually did this analysis, but I think it was how many times have you used marijuana in the last 6 months, okay? And we've got 3 independent variables: the peer delinquency score, age, and gender, right? Now, the second important thing you need to look at there is the coefficient. And the coefficient indicates 2 things. Number 1, the effect of that variable on the dependent variable, and 2, the direction. A positive number means a positive relationship, i.e., as that variable increases, the dependent variable increases. If it's a negative number, it's a negative relationship. In other words, if that variable decreases, the dependent variable increases. Or as that variable, as the independent variable increases, the dependent variable decreases, right? So, as you can see, the peer delinquency score and the gender variables are positive. So as that independent variable increases, the dependent variable increases. But the age variable is negative, meaning as age increases, marijuana use goes down within this sample, within this analysis, right? We're not necessarily talking about wider generalizability concerns here. We're focusing merely on this sample. But as in this sample, as age increased, marijuana use decreased, right? And same thing with gender. And gender, I believe, was measured as male equals 1, female equals 0. And you might be thinking, but Kevin, that's a dichotomous variable. And you said OLS can't use dichotomous variables. OLS cannot use dichotomous variables as a dependent variable. This is an independent variable. You can use dichotomous variables all you want. So with gender, 1 is male, 0 is female. That is a positive relationship. So in other words, the way to interpret that is males are more likely to smoke marijuana than females in this sample. But the age and gender were just kind of control variables. What we really wanted to know was whether peer delinquency increases or decreases marijuana use. We only put age and gender in there as controls, right? We're really interested in this peer delinquency score. And I forget exactly how that was calculated. Again, this was a long time ago. But it's basically just a measure of how delinquent your peers are. The people you hang out with, the people you spend time with. How delinquent are they? Are they doing bad things? Are they skipping school and graffitiing and smoking cigarettes and all those other delinquent things? We measured that using this survey, and now the peer delinquency score is positive and it's relatively large. The coefficient there is a relatively large number. So as your peers become more delinquent, as that peer delinquency score goes up, marijuana use also goes up, right? Now, is this statistically significant? Is this difference we see, is this relationship we see as one goes up, the other goes up, is that because it's actually happening? Or is this based on pure random chance? We happen to get a sample where they tended to correlate, but in reality, if we had gotten a much larger sample or a different sample, they would be completely unrelated. Is this observed relationship real? Or is it just purely due to chance? Well, we can calculate the odds that it's due to pure random chance. Okay? What are the odds that we would see what we're seeing here if there was no actual relationship in reality, and the only reason we're seeing what we see here is because by pure random chance we happen to get a sample that looked like this, right? And that is that P number over there on the far right. That P is the probability that we would be seeing what we're seeing if in reality there was no relationship between these two variables at all, right? And so to be statistically significant, that p-value needs to be at 0.05, i.e. 5%, or less. And in this case, the variable we're really interested in, our peer delinquency score, the probability that we would see this relationship between peer delinquency and marijuana use, if there was no relationship in reality and it was just pure random chance that we grabbed a sample that showed that correlation, is less than 0.001. So in other words, less than 0.1% of the time would we see these values if there was no actual correlation in the real world. Right? But remember, that only accounts for random error. This doesn't account for systematic error. If we made a systematic error in our sampling, this p-value is completely meaningless. This p-value only accounts for random error, which we can kind of estimate probabilistically. It doesn't account for systematic error, which we can't estimate at all. So assuming we did our sampling right, assuming we only have to worry about random error, the probability that we would see this relationship, if it was just by pure random chance we grabbed this sample and they had showed these numbers, is less than 0.1%. So that's small enough that we are confident that we can say that there is a statistically significant relationship between peer delinquency and marijuana use. Now, I hope that makes sense. I hope this wasn't too confusing. I know this kind of regression stuff is complicated. But once you kind of learn to interpret these graphs, because these graphs or these tables are everywhere in the published literature, right? And what you really need to pay attention to are the variables, both independent and dependent, the coefficient, both size and whether it's positive or negative, the p-value for each independent variable, and then some other things that you might be interested in are things like n. So you'll notice down there at the bottom, in almost the lower right, it says n equals 65. I said in an earlier section, n is the label we use for the size of our sample. So that n equals 65 means that we had 65 people in this sample. So it's a quick, easy way to say, oh, how big was their sample size? Oh, n equals 65, right there. We know this is based on data from 65 different teenagers, right? And then the r squared, that is how much of the dependent variable is explained by all of the independent variables combined, right? So in other words, if we wanted to predict your marijuana use rate, and the only thing we knew about you was your peer delinquency score, age, and gender, how accurate could we get? If all of those variables combine to explain 100%, like we can tell you exactly how much marijuana you use if we know those three independent variables, that would be an r squared of 1. If it doesn't tell us anything or tells us very minimal things, that number will get closer and smaller and closer to 0. So like an r squared of 0.02 is really low. It might be statistically significant, but it really doesn't explain much. There's obviously something else that is much more impactful on the dependent variable than whatever independent variables you're trying to score. So here an r squared of 0.78, meaning we're roughly 80% accurate. If we only know your peer delinquency score, your age, and your gender, we're like 80% accurate with how much marijuana you smoke. That is a really high r squared. That is a lot, right? But those are the really important things here on this table, especially if you're just getting started out in research methods, just getting started out in in understanding published research. Variables, coefficient size and direction, p-value, and maybe r-squared. Those are the really important things you need to look at, okay? Once you get more advanced, once you learn more statistics, you'll start understanding what all these other numbers mean and what they can tell you about these different factors and why they're important. But for beginners, for people just starting out with trying to understand research, those are the really important things you need to understand and need to be able to interpret at a quick glance at any table that you see in a published journal article. All right. That was a lot of information. Please, 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 if you're having questions, either watch the video again or find a way to contact me, message me, say, hey, Kevin, I'm still not understanding. I had this question. I would love to get back to you. But if you're still watching, I really appreciate it. Thank you so much, and I'll see you in the next one.